Hello, in this video we are going to look at Gibbs free energy for reactions that are not under standard states. So we learned how to calculate the Gibbs free energy under standard states. It was just delta H standard minus T delta S standard. And that was when the concentration of reactants and products, if they're both reactants, are 1 molar, products 1 molar if they're aqueous. If they were gaseous, both reactants and products should be their partial pressure should be 1 atmosphere. If they were solids or liquids, they should be pure. Now, what if the conditions are not standard? Because standard condition is just a very thin slice, just one slice in time where you have those concentrations. As soon as the reaction starts going, those concentrations change. Or even before, you may have different concentrations. Then how do you calculate the delta G? Remember, it's the delta G that tells you whether a reaction is spontaneous or not under the specified conditions, not delta G standard. Delta G standard only tells you whether the reaction is spontaneous or not under standard conditions, when the concentrations are 1 molar or the partial pressures are 1 atm. But what if the conditions were like that? Well, in that case, you calculate delta G by taking delta G standard. So you have to calculate delta G standard to get the delta G. So you first calculate delta G standard, and then to it you add RT natural log of Q. Q is the reaction quotient, and if you have gaseous items, then you use their partial pressures in atm. If you have aqueous items, then you use their concentrations in molarity. And T is temperature in Kelvin, and R is the ideal gas constant, 8.314, expressed in terms of joules. So that's how you would do it. So we always wanted to calculate delta G, but in order to do that, first we have to calculate delta G standard, so then we can figure out the delta G, and then from that figure out whether a reaction's spontaneous or not. So let's look at this example. The delta G standard for this reaction we've calculated in previous videos. It came out to be 130 kilojoules per mole. That means under standard conditions, which means when we have pure calcium oxide, pure calcium carbonate solids, and partial pressure of CO2 is 1 atmosphere above that, and temperature is 25 degrees Celsius. Under those conditions, the delta G for this reaction, which we call delta G standard, is plus 130 kilojoule per mole. So that means that this reaction is not spontaneous. And so in order to make it spontaneous, you have to actually, under those conditions, put in 100 kilojoules, minimum 100 kilojoules of work, energy in the form of work, to get it to become spontaneous. So now, we want to figure out what is the delta G if the partial pressure of CO2 is lower than 1 atmosphere. It's like 1 times 10 to the power minus 5 atmosphere, and the temperature is 25 degrees Celsius. Well, to calculate that, again, we use the formula, and I plug in the numbers. And of course, you're going to convert this into kilojoules. Don't forget, because this is in kilojoules. So then the delta G will be a little less positive. It's 101. So that means that it's still non-spontaneous under these conditions, but not as much as before. So under these conditions, if you wanted to make it spontaneous, we would have to put in only 101.5 kilojoules per mole of work minimum to get it to become spontaneous, rather than 130, which was previous. Now, what if we wanted to figure out what the delta G is under these conditions, which I wrote on the other side. So for part B, now let's see, if we decrease the partial pressure of CO2 and increase the temperature, the reaction becomes spontaneous. So now I am decreasing the partial pressure of CO2 to 1 times 10 to the power minus 20 atm. So you have very little CO2 there. And the temperature I increased it to 100 degrees Celsius. So then I plug in the numbers and I solve, and now we see that this term now becomes more negative than this is positive. So overall, the delta G will be negative. So under these conditions, the reaction is actually spontaneous. So whether the reaction is spontaneous or not greatly depends on the conditions, of course. So keep that in mind. Generally, as a reaction proceeds and reactants get converted into products, if initially the reaction is spontaneous, as the reaction proceeds, it becomes less and less spontaneous. Why? Because Q gets bigger and bigger, and as Q gets bigger and bigger, this term gets more and more positive. So even if delta G standard initially is negative, as this gets more positive, it will become bigger than that, and then eventually delta G becomes 0, which means you reach equilibrium. So in this case, for example, the reaction under these conditions is spontaneous, but as it proceeds, creates more and more CO2, so this partial pressure goes up. So as that goes up, this term becomes bigger, meaning it will be less and less negative, and then what happens is the reaction reaches equilibrium and the delta G becomes 0.